introducing my postdocs. It's a great pleasure to introduce him to his talk, Dr. Xinkun Brand. So Xinkun started his academic career at Nanjing University and received his bachelor degrees in chemistry and biochemistry in 2012. And after that, he did his graduate studies with Professor Lui Wang, University of Oxford, where he did some great work in engineering cytochrome P450 enzymes for production of drug metabolite. He also contributed to discover a new interesting reaction catalyzed by this class of enzymes. So Xinkun joined my group a couple of years ago, and we've been involved in our research developing new biocatalytic methods for biological carbon transfer reaction. As I hope you will see, so he's a fearless protein engineer and has done what I believe some outstanding work in expanding the scope of these methods to intramolecular cyclopropanational reaction, which for us has sort of opened a range of new opportunity in terms of method development, in terms of tackling other synthetic transformation using biocatalysis. So with that, I'd like to pass the word to Xinkun for his presentation.
Okay. Can everybody hear me? Yeah. Thanks to Rudy for the very kind introduction, and thanks to Professor Anthony Green and Alison Narayan for organizing this biocatalysis virtual symposium and giving me the opportunity to share some of my research on tailoring myoglobin carbene transferases for stereoselective intramolecular cyclopropanation reactions. Being the smallest all-carbon cyclic molecule, cyclopropane and cyclopropane-containing scaffolds have attracted significant research interest due to their prevalence in natural products and pharmaceuticals. Synthetic chemists have been searching for efficient and selective methods for their synthesis. As a researcher working in the biocatalysis field, I wanted to ask the question if we can make them by enzymes. In recent years, engineered hemoproteins have emerged as promising biocatalytic platforms for abiological cyclopropanation reactions. These reactions use a carbene transfer mechanism in which the diazo compound could act as the carbene donors. Upon the release of nitrogen, iron carbenoid electrophilic intermediates could be generated and then trapped by the olefin substrate to afford this cyclopropanation product. A number of hemoproteins have been developed, including cytochrome P450s and cytochrome P411s, pioneered by Arnold Group, as well as the myoglobin scaffold by our group, which was found to be a robust and versatile scaffold for carbene transfer reactions, and also other types of globin scaffolds. Another important strategy in the development is the development of artificial metalloproteins, including the iridium-based P450s by Harwick, the replacement of metals and synthetic cofactors of myoglobin by our group and Hayashi group, and some structurally distinct protein scaffold developed by Lewis group and Rolf's group. However, both of the hemoproteins and artificial metalloproteins were limited to only intermolecular reactions. So we wanted to challenge the intramolecular reaction because this transformation is a valuable strategy for the synthesis of cyclopropane fused bicyclic scaffold. By varying the chain lengths and the heteroatoms, cyclopropane fused lactone and lactams with different ring sizes could be achieved. However, achieving this task by enzymes is challenging. And the simplest reason is these substrates are more sterically demanding. And controlling the stereoselectivity could also be difficult since we need to control the orientation of both the diazo part and the olefin part within the same molecule. And our group has a research focus on engineering myoglobin for abiological reactions. Sperm whale myoglobin is an oxygen storage protein consisting of around 150 amino acid residues. It contains an iron proton porphyrin 9 heme cofactor, which is embedded within the protein through non-covalent interactions. Iron atom is coordinated to the protein through the side chain of a proximal histidine ligand. During the last 5 years, our group has successfully demonstrated that engineered myoglobins are capable of catalyzing the stereoselective and even enantiocomplementary intermolecular cyclopropanations of vinyl arenes and electron deficient olefins in the presence of diazo compound with varied alpha electron withdrawing groups, including the ester group, the CF3 group, and the cyano group. We wanted to see if these catalysts are transferable to the intramolecular reactions. We picked up wild-type myoglobin and two optimal variants for intermolecular cyclopropanation reactions, which showed perfect diastereoselectivity selectivity and high levels of complementary enantioselectivity. Then we tested these three catalysts towards the cyclization of our model compound, trans-cinnamol 2-diazoacetate, and found these catalysts were not as active and selective anymore. The double mutant showed 33% conversion, while the triple mutant could only give 20%. Regarding the enantioselectivity, there was no significant improvement compared to the wild type. And these results suggest that the optimal catalysts were not transferable between the inter and the intramolecular cycloproplanation reactions. And taking into consideration that both wild-type myoglobin and the double mutant gave good enantioselectivity, we decided to use them as the starting point for protein evolution. At first, we applied a rational approach using these two as the template by screening a mini library of alanine mutants targeting the active site residues. And fortunately, we were able to identify a triple mutant that could give the quantitative yield and 96% EE. And I was pretty happy at that moment with this rational approach. However, when I brought this result to my advisor, Rudy, he was not satisfied and asked me to find another catalyst that gave 99% enantioselectivity because the majority of the possible active site sequence space was not targeted yet. Then I applied a directed evolution approach, an active site mutational landscape library that contains all the possible 19 mutations at each of the 4 active site residues were created. And this double mutant H64V107S was then identified to give 78% yield and perfect 99% enantioselectivity under standard conditions. By performing conditions optimization in E. coli host cells, this catalyst could be tuned to give total conversion and 99% EE. The substrate scope was then explored under the optimal conditions and at preparative scales. Both electron withdrawing groups and electron donating groups were well tolerated. Substrates carrying paro, meta, and ortho substitutions on the phenyl rings were all efficiently cyclized, leading to the corresponding bicyclic product in good to quantitative yield. Good conversion and enantioselectivity was also achieved with the sterically demanding naphthalene-based substrate, as well as a heterocycle furan-based substrate, further highlighting the broad substrate scope for this of this methodology. And notably, across all the arrow substituted substrate, excellent levels of enantioselectivity were observed, with the lowest EE being 90%. As for the more challenging substrates with unactivated aliphatic olefins or multiple olefinic groups, lower enantioselectivity were observed, suggesting the different requirement of the protein chiral environment, and separate protein evolution studies are needed. We were also interested in making the opposite enantiomer, as mirror image forms of stereoisomers of bioactive compounds may have very distinct pharmacological effects. But achieving this task is difficult because wild-type myoglobin already has a strong preference towards the first enantiomer. Therefore, iterative rounds of site saturation mutagenesis targeting the active site residues were performed, and a progressive improvement of the desired selectivity towards the second enantiomer was then obtained through three rounds of optimization. The resulting triple mutant was able to give the second enantiomer in 89% EE, which equals to 94.5 to 5.5 enantiomeric ratio. This triple mutant was then assessed with the same panel of diazoacetate substrates I mentioned earlier, And interestingly, all of these substrates were converted to give enantiomer-rich products in 41 to 99% yield. All of the arrow-substituted substrates showed higher enantiomer selectivity than less activated aliphatic substrates, giving 96% EE to 90, giving 76% EE to 96% EE. And in all cases, we were able to obtain the second enantiomer as the major product, therefore furnishing a stereo-divergent catalyst for this intramolecular cyclopropanation reaction. And to gain more insights into the stereo-divergent catalyst, we then proposed a stereochemical model by mapping their mutations onto myoglobin structure. So in the first case, an enlarged cavity is created between the V68 and 107. And the distal mutation H64V acts as a gatekeeper to open up the cavity in the back so that the ester group can be accommodated. And the intramolecular attack to the reface of the carbene is therefore favored to give the 2A product. While in the second case, the bulky mutations H64W and V68F could block the cavity in the back, and therefore giving a different preference for the ester group to be accommodated. F43A mutation could create space for the phenyl group and facilitate the intramolecular attack to the side face of the carbene, therefore giving the access to the opposite enantiomer. While further computational and structural studies are needed to probe these stereochemical models, it is instructive to observe how complete remodeling of myoglobin active sites was required to achieve stereo-divergent reactivity. To further demonstrate the synthetic utility of the present strategy, we then performed a gram-scale synthesis with this dimethyl substituted allyl diazoacetate. This reaction enabled the selective synthesis of this dimethyl cyclopropane product in 81% EE and 83% isolated yield, which is a key intermediate that can be further elaborated for the synthesis of parenthroid natural products. On the other hand, we also explored the possibility to derivatize the bicyclic cyclopropyl-fused gamma lactones achieved from arrow-substituted substrates. With the enantiopure compound that was produced from our model substrate, we were able to perform different types of chemical transformations, including reduction, hydrolysis, and hydrogenolysis, to afford a variety of tri-substituted cyclopropanes with only minimal to no erosion of enantiopurity. So to sum up this project, the first biocatalytic example for the intramolecular cyclopropanation was accomplished through the engineering of myoglobin carbene transferases, and this method offers a new route to access a broad range of enantiomer-rich cyclopropane gamma lactones. As always being curious, we then asked the question if we can extend this methodology to expanded ring sizes, for example, to make the cyclopropane-fused 6-member lactones. Cyclopropane delta lactones are actually very valuable motifs that are found in many natural products and drugs. And there has been no satisfactory methodology for their synthesis. The only chemical method was reported by the Doyle group, in which they used a rhodium-based catalyst. And this method was limited by the narrow substrate scope and modest levels of enantiomer selectivity. And moreover, we think that shifting from 6-membered lactone to making, shifting from 5-membered lactone to making this 6-member lactone does not add too much difficulty in its chemistry. So, and we thought this is a perfect example to show the advantages of our biocatalysis over the conventional chemical approaches. However, when we started our research, we found it is very difficult. Firstly, the free cofactor hemine and iron TPP were not active towards this reaction, suggesting this reaction is energetically unfavorable. And none of our optimal catalysts for gamma lactone synthesis were active. We then screened more than 150 purified myoglobin variants and found the majority of them were inactive. So these results were very disappointing But when we look at the results from a different angle, there were at least 6 variants showing around 1% detectable activities. And interestingly, they feature a common mutation, which is the V68G, suggesting that this space-creating mutation might be necessary. So using the V68G as the starting point, we applied a similar evolution approach I mentioned earlier to improve the activity and enantiomer selectivity towards the formation of the same enantiomer as compared to the template V68G. 3 beneficial mutations were then accumulated, and the resulting culturable mutant was able to give 65% yield and perfect enantiomer selectivity. Following a different evolution trajectory, we were able to achieve the catalyst for making the opposite enantiomer in 99% EE. And the reaction conditions were further optimized, and the excellent levels of yields were achieved in both cases, with no erosion of the enantiomer selectivity. And this is actually a very good example to show how protein evolution can solve the problems in the real synthesis. The substrate scopes for both catalysts were then explored, and both catalysts were found to be pretty general, tolerating a broad range of substrates with electron withdrawing group and electron donating groups, and at different positions. The first catalyst showed 90 to 99% EE across all the substrate, while the second catalyst displayed slightly lower EE, ranging from 73% to 99%, with the only exception being 51% for the aliphatic substrate. After solving the problems for making cyclopropane fused gamma and delta lactones, we finally wanted to expand this methodology to cyclopropane gamma lactams, which can be derivatized to their corresponding pyrrolidines as important building blocks for natural product and drugs. Using this fluorinated allodiazoestamide as the model compound, we were able to achieve progressive improvement of product formation and enantiomer selectivity towards this cyclopropanation product. The resulting culturable mutant was able to give 99% conversion and 99% EE towards our model compound. And this catalyst also showed good substrate tolerance, giving 90% EE and to 99% EE across all the substrates. Interestingly, this catalyst can not only tolerate the substitutions on the phenyl ring, like other catalysts developed for lactones. It can also tolerate various N substitutions, including the methyl, methoxy group, ethyl group, free NH group, albeit in lower yield, allyl group, and even bulkier phenyl group. So to conclude my presentation for today, serial selective intramolecular cyclopropanations were achieved by tailoring myoglobin carbene transferases. These methodologies could offer new routes for the asymmetric construction of cyclopropane fused ring systems, including gamma lactones, delta lactones, and gamma lactams. We also learned that myoglobin is a remarkably versatile carbene transferase that can be trained for both inter and intramolecular cyclopropination reactions. Taking the advantage of the solvent-exposed active site, it can act as general catalyst to tolerate a broad substrate, a broad scope of substrates. But one thing we need to keep in mind is that for each specific transformation, we need to evolve a specific catalyst because the stereo control from enzymes are very precise. And this work opens up a lot of new opportunities for our group to develop other types of intramolecular carbene transfer reactions. Finally, I would like to thank University of Rochester and all the members from Fassan Group for the support, especially to Professor Rudy Fassan for always giving me very helpful advices, and Dr. Ajay and Ning Yu for being very collaborative and helping me on the synthesis of the diazo compounds for these projects. And I would be happy to take any of your questions. Thanks.
Okay, thanks very much, Xinkun, for a fantastic talk, a very impressive body of work. I'm going to hand over to Andrew to coordinate the questions, and Anya, if that's okay.
Okay, sure.
Yeah, so we've got a couple questions here. Just a quick reminder, please use the Q&A function for questions so that we don't have to go back
Q&A.
to
Yeah,
the chat
sure.
window. And
Okay, thanks.
that's it. But absolutely fine. So Terry asks, were any cis alkene substrates tried in this project?
Sorry.
Can you hear me?
It was like not very clear.
Sorry.
Yeah.
Terry asks, were any cis alkene substrates tried in this project?
Yeah, that's actually a good question. We did try some cis substrates, and we haven't got a very selective catalyst to make or maybe a catalyst to give a very high EE or DE towards a specific product. And the reasons might be there might be a few different reasons. One is because of the steric effects. The other one might be because of the mechanistic. I would say, yeah, the mechanism of our carbene transferase that can undergo either concerted mechanism or a radical-based mechanism. That's actually a very good question.
Great. Maybe a couple more. Melanie Hall asks, Xinkun, could you please comment on the requirements for sodium dithionate in your reaction?
Yeah, as for the reactions in E. coli host cells, we don't need to use the sodium dithionate. And we are taking the advantage from the reducing environment inside the cell.
Great.
Yeah. Any other questions?
Tristan Durand asks, could you comment on how quickly you screen libraries for EE? Chiral chromatography often requires long methods.
In general, our screening method is around like 20 to 30 minutes because we have to use a chiral column to separate the enantiomers, and it's not super easy. But what we can do is that we can use, we can try different substrate at the beginning and see which ones can be separated better with a shorter program. In this case, we can save a lot of time.